All right, guys, welcome back. This is Mr. Sheeling here with the rest of the Unit 6.2 notes example problems for stoichiometry. So just real quick, depending on how long it was since you last watched that video concerning the notes, remember I told you that I was going to come back and finish these problems. But before I start doing that, remember what I did. What I also did tell you was the fact that I wanted you to work on these on your own. So we did these two together. We went through, I talked about all this good stuff up here. You've got the graphic organizer already set to go. You've been using it, and you gave it a good whack. You gave example 3 a good try. You gave example 4 and 5 a good try. If you have not done that already, I need you to pause the video and you need to complete those on your own, okay? Preferably on a separate piece of paper. Here is fine too, but arguably should be on a separate piece of paper because we should have the correct answers here in the notes so that we don't confuse ourselves in the future. So again, if you haven't done these, pause the video, complete them, and then after you're done with that, after you've given it a good try, then come back and see what's supposed to happen, see how it is that I put these together, how you're supposed to put these together, see how correct you were, how off you were, okay? Okay, cool. So I'm hoping that the rest of us here, or now we are all here, I should say, ready to go, ready to finish this out. So let's do that. All right, so example 3, determine the mass of carbon dioxide produced when 0.85 grams of butane, C4H10, reacts with oxygen gas according to the following equation. So we've got this equation here, and it's asking us directly, what's the mass of carbon dioxide? What's the mass of my carbon dioxide when there is roughly about 0.85 grams of butane, this stuff right here, put into the system? Now, this is a good example where we don't want to get ourselves confused. Okay, so in this problem it says that, yeah, mass of carbon dioxide produced when 0.85 grams of butane reacts with oxygen gas. So it may look like this question is telling you, hey, oxygen gas has to do something with this whole thing. Like, we need to calculate oxygen gas in here. No. Again, all that's saying, this portion right here, all it's telling you is the fact that butane reacts with oxygen. We don't have to do anything with oxygen mathematically in order to complete this. Why? Because the ratios are still the same. Because we're going to be using the molar ratios, using the coefficients here in our balance equation to figure out, yeah, how much this stuff was produced. Because again, 2 of these will always react with 13 of these. Okay? So we don't have to worry about this. We don't have to worry specifically about this guy. We just have to worry about these two. And more specifically, we're going from here to here. We're going from grams of butane to mass of carbon dioxide. So we're going from mass of one substance to the mass of another. So I'm not going to go flip back and forth between the graphic organizer here. If you still want to, if you want to refresh on that, go back to the video, the lecture video concerning these notes, where I kind of show you how I use the graphic organizer in order to go from point A to point B. So let's get going. Okay, so we're given this. Our measurement given here is 0.85 grams of butane, which is C4H10. Put that over 1. Okay. And then I'm going from grams of one substance, and now I got to go from grams of this substance to moles of the same substance. So I'm going to quick figure out what the molar mass of butane is, and I'm going to find out it's 58.0 grams. Okay. And in that, there's always just 1 mole. So 1 mole of butane contains 58.0 grams of butane. Okay, so this would cancel out, that would cancel out this, so my new units are moles of butane. And then, now I have moles of this substance. I'll use my molar ratio to go from moles of this to moles of CO2. So I'm going to put, let's see, and I've got, my ratio is 2 to 8, so there's 2 moles of butane for every 8 moles of CO2. Okay, that cancels out, this. Now I'm left with moles of CO2. Okay, so if I were to solve for this, I would have moles of CO2, so I've got to go one more step, because now I got to go from moles of CO2 into mass of CO2. So in every 1 mole of CO2, there is a molar mass of 44 grams of CO2. Okay, so moles would cancel out, CO2 would cancel out, and I'm left with grams of CO2. I'm going to multiply across the top, multiply across the bottom, divide top from bottom, and then I'll end up with this. And keeping with 2 sig figs that we started with, my answer here would be roughly about 2.6 grams of CO2. Okay, roughly speaking. So what did we just say? Well, we said here that, well, if we input 0.85 grams of this stuff into our system, okay, into our problem here, okay, we should have a product here, mass of the product of our CO2. It should be 2.6 grams worth of CO2 produced. Okay, so that's what we just said there. So now example 4, determine the number of formula units, okay, of nickel 2 nitrate needed to produce 7.45 times 10 to the 25th formula units of sodium nitrate according to the following situation. Okay, so determine the number of formula units. So we're looking for particles of nickel nitrate. So we've got to figure out which one of these guys is nickel nitrate. Now, we can first kind of deduce the fact that nickel nitrate is probably one of the reactants, because it says here, determine the number of formula units needed in order to produce, so that should tell us it should be over here, because it's saying, well, if you want to make this much of sodium nitrate, you need this much stuff to start with. So we should suspect that it's over here. And then when we look at these, between these two, we can say, well, I know that's not nickel, that's sodium, okay? And it says nickel nitrate. Well, I know that's nickel. That's nitrate. I recognize that. Okay, so that is my nickel nitrate right there. Okay, so we're working with this stuff. And then it says here, in order to produce this amount of formula units of sodium nitrate. So I'm going to look, and it says to produce, so that tells me it's on the product side. So then I just look, am I talking about this guy? No, because that's nickel hydroxide, and I don't want that. What about this guy? That's sodium, definitely, and that looks like nitrate. So I think it's this stuff right here, okay, which is that it would be exactly right. So, okay, now where am I starting? Well, I'm starting with the measured amount, and we've got to know, or this is the expected measure amount that we want to come out, so we've got to know how much of this stuff we got to put in first. So we're going from here to here, going from particles of this stuff to particles of this stuff, okay? So let's write down what was given to us. So 7.45 times 10, I don't know why that dot's there, 7.45 times 10 to the 25th formula units of sodium nitrate, which is NaNO3, over 1, okay? And now I've got to convert this from particles to moles of the same substance, so NaO3. I'm going to put FUs of NaNO3. And here would be where we use Avogadro's number. And in every 1 mole, there's always that number. There's always Avogadro's number. Okay, so then this would cancel out, that cancels out, this cancels out, that cancels out, and we'd be left with moles of sodium nitrate. Okay. And so now we've got moles of substance A. We need to change that from moles of substance A to moles of substance B. So I'm going to put, let's see, now going to figure out what my molar ratio is here, and it looks like it's 2 of my sodium nitrate to 1 of my nickel nitrate. So it's going to be 2 moles of sodium nitrate to 1 mole of nickel nitrate. That cancels out, that cancels out, this cancels, that cancels. I'd be left with just moles of nickel nitrate. Oop, we're not done yet, because now I got to get this to particles of nickel nitrate. So I need to get rid of moles, so I'm going to have moles on the bottom. And then I'm going to have Avogadro's number up top, because I have to get this back to particles. And more specifically, I've got to get this back to formula units of nickel nitrate. So moles cancel out, this cancels out, and I'm left with this number of formula units of nickel nitrate after I multiply across the top, multiply across the bottom, divide top from bottom. My answer here would be, keeping sig figs, which is 3, keeping sig figs, my answer would be 3.73 times 10 to the 25th formula units of nickel nitrate. I'd have my answer. Okay. Okay. And then example 5. So determine the number of molecules of oxygen gas needed to combust 134 grams of magnesium, according to this equation. So not too bad. This is actually quite simple. Now, but this is that tricky one that I mentioned in the previous video. We have a diatom, and we're going to be working with a diatom, so we have to make sure we get all this good and correct. So, because what it's asking here is a number of molecules. Let's see, magnesium. Oh, man, shoot. I'm eating my words now because that's actually not true because we're starting with magnesium. Darn. So, forget what I just said, but still, the message still applies. You've got to watch out for these guys because the molar mass of this isn't 16.0 grams per mole. The molar mass of that guy is 32 grams per mole because it's 2 atoms of oxygen that form a molecule here. Okay, so it's double the mass. So it's 16 times 2, it's 32 grams per mole for that guy. Which we don't need to know for this particular question, but it is super duper important if we had to go from mass of this to mass of this. But we're only going from mass of this to particles of this. So it doesn't really matter. So, okay, anyway, so what are we working with? So determine the number of molecules of oxygen gas. So we're working with this guy. Needed to combust with 134 grams of magnesium. Just that guy, because that's magnesium oxide, okay? Also, the language here kind of tells us what's happening. So determine the number of molecules of oxygen gas needed to combust this, this material. So when you see that phraseology, need to combust, okay, that means that it's usually, that sounds like that's on the reactant side, okay? Because you're adding two things together, and then you should expect to say, well, if these two things come together, that should yield something, especially when it combusts, okay? So that's how we know where to kind of find them in this equation, and then obviously magnesium is very different from oxygen in its symbolism, okay? Okay, so let's now kind of write this down. So what are we given? Well, we're given 134 grams of magnesium. And we're trying to convert mass of this substance to particles of this substance. Okay. So we've got to first convert this from grams, from mass of magnesium, into moles of magnesium. So magnesium, looking at my periodic table, shows me that I've got 24.3 grams of magnesium. And we know molar mass is determined by this, that 1 mole of magnesium is there's going to be 24.3 grams of magnesium. That cancels out, that cancels out, this cancels out, that cancels out, and I'm left with moles of magnesium now. Okay, so I've got moles of magnesium. Now I have to convert moles of magnesium into moles of oxygen gas. So in order to do that, I need to use my handy dandy molar ratio. And there's two moles of magnesium to every 1 mole of oxygen. So I'm going to put 2 in the bottom here because I got to get rid of moles of magnesium. And I'm converting it into moles of O2. So that cancels out, this cancels, and I'd be left with moles of O2. I still have to go a step further because now I got to go from moles of O2 into particles of O2, specifically molecules of O2. Okay, so then it would look like this. I'm going to put 1 mole of O2 because I got to get rid of moles of O2 and replace it with molecules of O2. And in order to do that, I have to use Avogadro's number. So this cancels out because of this, that cancels out because of that, and I'd be left with moles or molecules of O2. I'm going to multiply across the top, multiply across the bottom, divide top from bottom, and then this is what we should get. We should get 1.66 times 10 to the 24th molecules of O2. Keeping with the same number of sig figs, because we have 3 here, should have 3 here, okay? Molecules of O2, and I'm showing all my work, all good, and this would be the correct answer. So that is the rest of the examples here, guys. Nothing really else to talk about. If you still have questions, if you need help, get a hold of me. Fridays are available for you guys to come in to get that extra help. I'm also open for Google Meets. So if you want to schedule a Google Meet, so let's say if you don't want to come in, let's say you'd rather just stay home, that's fine too. We can schedule some Google Meets. Just reach out to me and let me know what you want to do. Because again, like this is super, this isn't, or this is something you have to get, okay? And so if we're struggling here, we can't move on to BCA charts. We can't move on to the next section of this unit. So make sure you reach out to me, get that help so that we can keep moving forward and do the best that we can. All right, guys, that's it. So I'll see you in the next one.